Okay, in this video lesson, we're going to talk about the size of an atom, okay? So first thing, the way that chemists have figured out the size of atoms is we use something called X-ray crystallography. And what we've done is basically it's a fancy type of X-ray machine that can look down at the atomic level. And they send a beam of X-rays into these atoms, and they bounce off the two nuclei, not unlike the gold foil experiment that Rutherford did to find the actual nucleus of the atom, okay? And because the X-rays bounce off the nucleus, but they pass through the electron clouds, we can pinpoint one nucleus to the other nucleus, and as a result, we can start to map out distances between them, okay? So it's not an easy process, but we can actually measure kind of indirectly the distance between two nuclei and then divide that by how many are there and the size of in between those and figure out how far apart they are or how big they are, okay? So if we take a look at this graphic, this shows us kind of where the size of the atoms are. So these numbers here are in picometers, okay? Picometers are times 10 to the negative 12th of a meter. So they're 1/1000th of a meter in size, okay? So imagine taking like a yardstick or a meter stick and cutting into 1,000,000,000 slices. 1 picometer is one of those slices, okay? So if we look, each circle represents that size also relatively for us. And it, if we take a look, we have two questions down here. So what type of element tends to be larger? So remember, we have our metals over here, and we have our non-metals here. So if we look, it's pretty generally speaking that the metals in this area here tend to be larger, okay? And then our non-metals over here tend to be smaller, okay? Now that's important because the way they bond is going to be related to their size and how they are. And then if we look even more particular, we notice that the actual size of the atom gets bigger as we go down the table here, okay? And that would make sense because every time you go down a row, we have a new energy level, another energy level, another energy level, another energy level, okay? So it would make sense that, something like sodium is going to be smaller than something like potassium because sodium, there's only 3 energy levels around it, and potassium has 4 energy levels around it, okay? And then rubidium has 5 energy levels and so forth because, this is our first energy level, second energy level, third energy level, fourth energy level, okay? So they get bigger as they have more energy levels. Now we notice over here, they actually get smaller as you go to the right. And that's because when you get more electrons and more protons on the same energy level, they actually kind of crunch down tighter, like pulling things together, like squishing things down tighter, okay? So our biggest elements are in the bottom left. Our smallest elements are in the top right of our periodic table. So why does size matter to us? Okay, so as chemists, why do we care the size of an atom? Well, in terms of reactivity or how easily something loses or gains electrons, our biggest atoms and our smallest atoms are the most reactive, okay? So the way you become more reactive is to get very big or to be very small, okay? So our halogens, if we go back and look, the halogens are kind of our smallest of our non-metals that are not noble gases. So in this row, this is the biggest, this is the smallest. So the halogen would be the smallest within this row. The halogen is the smallest within this row, and so forth. So our halogens being the smallest are then become our most reactive non-metals, okay? Now, the reason why is because they're really good at taking electrons from other atoms because they're small. The alkali metals on the other side are our most reactive metals, okay, because they're very big. So they're good at letting electrons leave. So if we take a look, cesium, rubidium, potassium, sodium, they're our biggest metals. So they're really good at letting electrons go, okay? So keeping that in mind, we could take a look at this graphic over here and kind of show why that is, okay? So on the left-hand side over here, we have fluorine. And fluorine is very, very small. And because it's so small, its nucleus right here is really close to its outer energy level. So it has a small distance between its outer energy levels. Where francium is very big, and its nucleus, which is right here, is a long ways away from its last electron, okay? So if these two things come into contact, or if these two things collide with each other, and this electron here that was originally francium's electron, that that electron has a decision to make. Not really a decision, but it's going to have a deal. It's either going to stay with francium or it's going to join fluorine. Well, francium its nucleus is what holds everything in. So this nucleus is pulling everything in because of those protons. Fluorine's nucleus is doing the same thing, pulling everything in. But fluorine's nucleus is so much closer. So because fluorine's nucleus is closer, it's going to pull this electron, and it's going to take that electron away. So as a result, francium will end up losing an electron. So it'll lose its energy level, and it'll become a positive charge. And then the fluorine, let me erase a little bit of this stuff so it's easier for us to see. Okay. The fluorine is going to gain that electron, and it's going to become a -1 charge. It's going to gain this extra electron right here. Okay? So between the two, the big atom lost the electron easy, and the small atom gained it easy. Okay, which makes them both reactive, but just in a different way. Where this one is losing to be reactive, here, this one is gaining to be reactive because of their size. Okay? So that's kind of works. So keeping that in mind, which element is the most reactive nonmetal? Okay, so let's go back again. So if small makes you reactive, which of these elements over here is the most reactive nonmetal? Okay, now keep in mind, it can't be any of these because these are our noble gases. Okay, so it can't be these. So we got to find the smallest one. Well, 42 is our smallest number, so fluorine is our most reactive nonmetal because noble gases are not reactive. Okay, so fluorine would be the answer to that one. Okay. And then the other answer, the other question asked is which element is the most reactive metal? Okay, so for metals we want to be big. Okay, so we go over here and we find our biggest of our nonmetals. Now on this periodic table it's cesium, but we do know that there's actually another row down here that just this periodic table just doesn't show us. And that extra row would have francium down here. Okay, so using the periodic tables that we hand out in class, we would say francium. On this table, it would be cesium, but the cesium one, this table doesn't show it all. So we want to make sure that we say that's francium because it is going to be our biggest of our metals, okay? So if we ask why, so why is fluorine the most reactive? Well, it's the smallest of our nonmetals. Why is francium the most reactive? It's the biggest of our nonmetals. Fluorine is really good at taking electrons. Francium is really good at giving them away, okay? Now, we have a name for that idea of the battle between gaining electrons and losing electrons, okay? We call that electronegativity, okay? Or the ability of an atom to gain and hold on to an electron when bonding with another atom. So who's really good at gaining the electrons? So we're going to focus all on gaining electrons here. It's a 0 to 4 scale, 4 being the best. There's no label to this. Just a ranking system, kind of like your GPAs, okay? So if you want to gain an electron, you need to be small and unstable, okay? So where do we have the smallest atoms that are the most unstable, okay? Well, let's go back to our periodic table again. Here's our smallest atoms in this corner up here, and these are the ones that are unstable. Remember, these are stable because they have full electrons. So nitrogen, oxygen, fluorine, chlorine, sulfur, you know, these elements in this corner are our smallest elements, and they are also our unstable ones, okay? So those nonmetals in that upper right-hand corner, they're going to be the ones that are really good at gaining electrons. So we'd say would have high electronegativity. So what would be really bad at gaining electrons? Well, that would be the opposite, right? So small and unstable is really good at gaining electrons. Big is bad at gaining electrons. Big is good at giving them. So, all right. So the metals would be very bad at gaining electrons, okay? Now, here's the actual trend. If we take a look at it, you'll notice francium, cesium down in this corner, very, very small numbers. They're not good at gaining electrons at all. As we move across the table, generally speaking, you know, they stay pretty flat through most of the transition metals, and then they spike, and they get much higher here. Notice how fluorine is the most electronegative element, which means it is the best at gaining electrons. Okay, cesium and francium are the worst at it, so they're going to be the ones who give away their electrons the most. So these give, these take. Okay, in terms of how electrons move if they're going to bond with each other. Okay, so we see that the electronegativity also gets higher as you go up every column because these are the smallest of our elements. Okay, so the smaller the element, the better it is at gaining electrons. The bigger the element, the worse it is at gaining electrons. Okay. Let's draw some conclusions and talk about why. So we know groups 15 to 17 gain electrons to form anions with a negative charge. Okay, so we're talking about the nonmetals in the right-hand side of the periodic table. They gain electrons and they form anions. Well, why do they do that? Well, they're the smallest elements. Okay. Sometimes teachers talk about they have 7 valence electrons or 6 valence electrons and they want 1 versus giving away 7, which is not really wrong, but it's not really why. It's just a mechanism of what happens. The reason why they gain electrons, the reason why they become anions, is because they are small, okay? And they have what's called high electronegativity, okay? So our final answer here is nonmetals are really good at gaining electrons because they are small, okay? When they do, they become negatively charged ions. If we flip it around, we know that groups 1 through 13 lose electrons to form cations with a positive charge. Okay, so why do they do that? Well, big elements are bad at gaining electrons. Okay, so if they're bad at gaining, that means they're good at giving them away, the opposite. Okay, so metals tend to be bigger. Okay, so metals won't gain electrons. Instead, they're good at losing electrons because they are big. Okay, when they do so, they become positively charged ions. Okay, so the take-home message is this: if you are a small atom, you're going to gain electrons and become a negative ion. If you are a big atom, you're going to lose electrons and become a positive ion. Okay? Nonmetals are small, so that way we can say nonmetals become negative ions. Metals are big, so we can say that metals are going to become positive ions. So we knew this already. We knew the charges from last unit, but this is just kind of the learning of why the charges are the way they are has to do with the size of the atom and the resulting electronegativities that they have. All right, that's it.